Hey guys, and welcome back. Today we're going to be talking about defining a linear function rule, so actually coming up with the rules ourselves. Today's learning target, again, we're going to determine if a relation is a function. We're going to get really specific on that and actually talk about what kind of equations are going to create, we're going to create from tables and graphs. So our success criteria is to create relationships that represent functions and determine if they're linear or nonlinear. So don't forget what we learned yesterday. So to start off, let's talk about what a linear function is and what a linear function rule is. When I say the word rule, I really just mean equation. That's what rule means. We're going to create an equation that all the points can abide by. So a linear function is a function whose graph is a straight line. We know that from yesterday. A linear function rule is going to be an equation that describes a linear function. So for instance, this equation right here, y equals x plus 4. If I were to create a table from that equation and just generate some inputs, let's say I want to know what the outputs are when the inputs are -2, -1, 0, and 1. Okay, so if I were to plug -2 in for the x in this equation, okay, and actually I'm gonna color code this just so you can see exactly what I've plugged in. I'm plugging in -2 where x once was. So really this does say y equals x plus 4, but I've plugged in this -2 right there in for where x is in the equation. So really y is equal to 2. The output is 2 when the input is -2. So I'm going to write 2 in my table. Now I'm just going to continue that, that process where I'm plugging in numbers for x. So now I'm plugging in -1. And then I want to add 4 to that. -1 plus 4 is 3. So I'm going to put 3 in my output column. And I'm going to continue that. I'm just not going to show the work that, that goes along with it. I'm just going to fill in the table because you can do this mentally as well. So if I were to do 0 plus 4, that's 4, and 1 plus 4 would be 5. Now let's check the graph to see if those points are there. So I'm looking for -2, 2. So -2, 2 is right here. I'm looking for -1, 3, 0, 4. Okay, so -1, 3, that's about there. 0, 4, that's right there. And then my last point was 1, 5. So it seems like all the points that I generated lie on the line of that graph. And that's really what's going on here is we should be able to create a table from what you see in the graph and then decide, how do I go from x to y? What do I have to do to -2 to get it to become a 2? Well, I could add 4 and then make sure that that rule is the same throughout all of the inputs. It's a pattern. -1 plus 4 is 3. 0 plus 4 is 4. 1 plus 4 is 5. So this would be the rule that all the inputs and the outputs are following. Now, I'm going to just introduce you to functions like this. This is a nonlinear function. We're not going to be studying it, but you should be able to recognize it. This is called an absolute value graph. Okay, those two bars mean absolute value, and that just means whatever you plug into x, a positive value will come out. That's why even though you see negative x's, the line is still positive as it goes back. So this is the graph of an absolute value, and even though it's nonlinear, it's still a function because it passes the vertical line test. And then this is kind of a special linear case as well, x equals 4. Things to remember when you just have x equals a number or y equals a number are that no matter how you create the table, you should always have that number in for that variable. So I could create a table here where all I'm doing is writing 4s for x because that's what that equation means, that x is always 4. So I made all the inputs 4, and it doesn't matter what I put for the outputs. I could put -11, I could put 0, I could 5 or 7. It doesn't matter because they always need to be 4. That's what that equation is describing. So let's take a look at the first example. We're going to decide, here's our equation bank right here. They gave us some options to choose from. I want to know which equation describes each one of these graphs. So I'm just going to pull 3 to 4 points off of the graph, and then I'm going to see how I'm supposed to go from input to output. So I'm going to mark on the graph here some integer value points first. Okay, so those are all integer value points, and I'm going to place them in my table. So I've got -2, -2. Oop. See, I've got -1, -1. 0, 0, 1, 1, and 2, 2. Okay, now if I want to describe the pattern that is happening to go from input to output, it just seems like all the x's are the same as all of the y's. So y is equal to x. And I'm seeing that equation right there. So I'm going to write that on the line, that this equation is y equals x. So now let's take a look at the second one and see what we can come up with. Okay, I'm going to mark a few points on the graph, make sure I'm reading it right. I see an integer value there, 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 and there. Okay, so now I'm going to read them, put them in a table, and hopefully I'll be able to decide how I go from input to output. Okay, so I'm reading -2, +2. -1, +1, 0, 0, 1, -1, and 2, -2. So while the digits are staying the same from input to output, it seems like they're the opposite. Okay, and whenever we have the opposite, we're really multiplying them by -1. So this is y is equal to -x. So if I were to plug in -2, negative of -2 is +2. So it makes sense that we're just creating the opposite. And really, anytime you make something negative, that means the opposite. Okay, so I have one more graph that I need to do this for. Again, I'm going to read some integer value points off of this. Here I can only really see 3 integer value points. And I'm reading them to be -1, -2, 0, 0, and 1, 2. So on that one, I need to describe some pattern that is happening to go from input to output. Well, it looks like I'm multiplying it by 2 each time. So in order to go from -1 to -2, that seems like we just need to multiply by 2. Now you can think about a couple of different things. So the first thing that popped into my head was multiply by 2. Okay. Another thing you may think of is, well, what if I subtracted 1? Because -1 minus 1 is -2. However, that does not suit 0, 0 or 1, 2. 0 minus 1 is -1, not 0. And 1 minus 1 is 0, not 2. So -1 actually doesn't work here. If there's any other patterns that you see that you think might happen, just make sure it works for all points. But it seems like multiplying all the inputs by 2 is going to work for all of the different points that I've pointed out here. So this equation is going to be y is equal to 2 times x. All you have to do is take the x and multiply it by 2. So why don't you guys go ahead and try this on your U-Try. Take out a couple of points and see if you can find a pattern that would get you the function rule. Alright, so now we're going to go ahead with another example, but first I have to intro you guys to different types of forms of equations. We did not talk about what equations look like when they're linear or nonlinear. So let's talk about my list of linear equations. If we were to make tables for any one of these equations, you would be able to see that the rate of change is constant. Remember, for a linear function, the rate of change is constant or unchanging, whereas a nonlinear function, the rate of change is not constant. Okay, so I'm going to show you what I mean here by testing, let's say, this first equation. So my input would be A, my output would be B. Let's say I have -1, 0, 1, 2, 3 as some inputs just to see what happens when I put them into the function. So if I were to plug -1 in for A, I would get B is equal to 7 minus -1. And minusing a -1 is the same as adding a positive. So that would mean B is equal to 8. So my output for -1 would be 8. So now I'm just going to continue doing that work, only I'm going to mentally plug in all the other numbers. So 7 minus 0 is going to be 7. 7 minus 1 is going to be 6. 7 minus 2 is 5. 7 minus 3 is 4. So now I can see my inputs, I deliberately was increasing by 1. So that's good. And then my outputs, those are also, actually, they're not increasing, they're decreasing by 1. So 8 minus 1 is 7. 7 minus 1 is 6. 6 minus 1 is 5, and so on. So my rate of change is the same. It's always going to be -1 over 1, or just -1. Now I can do the same thing and create tables for all of those guys, but I don't have to. What you need to remember is anything in the form y equals mx, now I'm going to add this, plus anything else is going to be a linear function. So before we only had y equals mx, and we are going to dive into this plus b part that's there. But if you ever see this form y equals mx, and if you see anything added to it, that's going to be a linear equation. Another way to remember this is if you don't see any exponents. Okay, so no exponents. That's one way to identify. No variables on denominator. Let's see, and no strange or some symbols that you don't recognize. So bringing you to kind of like this example right here, okay, that's our absolute value graph. That is not going to be something linear, okay. We again want to look for y equals mx plus b. So anything like a equals s squared, that has an exponent, that's not going to be linear. And then y equals 5 over x, the variable is on the denominator, so that's not going to be linear. Again, looking for y equals mx plus b. So let's take a look at the second example. It says, is each function rule linear or nonlinear? So this is just identification. So I'm going to write I'm just going to first recognize where are the y equals mx plus b's. If there's any of those, I'm going to write linear on it. Okay, so I'm seeing here's y equals mx. Okay, so that's linear. Okay, y equals 4x. That's the same thing as y equals mx plus b. It would just be plus 0 on the end. Okay, and then let's see, I see another y equals mx right here. Okay, y equals negative 3x. And then I see this one over here, the last one, y equals x minus 2. That's in y equals mx plus b form. So now all of the other ones that are on here, this one, the first one has an exponent, so that, as we said, was nonlinear. And this last one over here has a variable on the bottom, so that's nonlinear as well. Okay, anytime you're looking for linearity, y equals mx plus b form. That's what we want. So why don't you go ahead and try to tell me now which one of these you think are linear functions. All right, so the main idea that we've been practicing so far today is really just these function rule rules. So just to illustrate the main concept of today, if we have a dog walker that earns $10 plus $3 per dog, so she already earns $10 right off the bat just for doing her job, and then she could be walking 1 dog, she could be walking 5 dogs, she could be walking 10 dogs, so she gets paid $3 for every dog she has to walk, which makes sense because it gets harder the more dogs you have, so she's going to add $3 every time she has another dog, which if we look at the equation that represents this function, if we call M the money earned and we call D the number of dogs being walked, that's what this equation is saying. The money she earns, or the money she makes, is going to be her initial fee of $10 plus $3 per, meaning multiply, dog. Okay, and I'm actually going to write that out in words. So, okay, it equals a $10 fee plus $3 per dog. Okay, so these are the words that translate that equation. Okay, so the function in this case represents M equals 10 plus 3D. So if we were to plug in, let's say she's walking 3 dogs. Well, you would plug in 3 into the input, which is the letter or variable D. So M equals 10 plus 3, and then instead of D for dog, we should plug in 3 because she's walking 3 dogs. Now we start to simplify. Okay, first, whenever we simplify, you should do multiplication first. So that gives me M is equal to 10 plus 9, which means that day she's going to be making $19, which is exactly what came out in the output. Okay, so for every input, you plug into the function rule that we learned how to create in the past, in example 1. You plug into the rule, and that will give you your output. So let's take a look at the third example. It says a swimmer burns 8.8 calories per minute while swimming laps. Which function rule describes how many calories C the swimmer burns during any number of minutes M? So again, let's review which one would be the independent, which one would be the dependent, which one would be the input, and which one would be the output. So let's review here. We have independent variables, which we said were X variables, okay, or because usually we call them X or Y. This time we're going to be talking about them in terms of C and M. Okay, so we have independent, which are the inputs. Okay, and those are the ones that don't rely on anything. Then we have our dependents, and those are going to be our outputs. Okay, inputs we choose. Outputs, those are generated, meaning you need an input in order to get the output. Okay, so in our situation, I'm going to highlight what our 2 variables are here. I have calories, how many calories, C, and I have number of minutes, M. So it seems to me like the independent variable is going to be the number of minutes, because time usually goes by, and it doesn't depend on anything else. It just goes. Nothing else influences time. But the time is definitely going to influence how many calories you burn. So since the number of calories depend on how many minutes you've been swimming for, I'm going to say that the independent variable, or the inputs, is going to be the minutes M. And the dependent, or the outputs, that's going to be calories, or C. So when I create my equation, all of my equations so far have looked like y equals mx, and then we just talked about how you can always add something to that as well, so the plus b. Okay, well, the output is usually the y, or it should always be the y, and the input is the x. So I'm going to use the variables that they told me to use, c and m. So instead of y, I'm going to write c. I still need to find my slope, or my rate of change, m, and then my x is actually going to be m as well. So I'm not going to write m times m. I'm going to write, let's see, we need to find our slope, which it says, I'm going to put a blank, okay, and then we need to times it by m. And then it doesn't say we need to add anything to it, so I'm just going to keep it in y equals mx form. So we need to figure out what we need to put in for the rate of change, or the slope here. And if we look, it says a swimmer burns 8.8 calories per minute. Per minute. That indicates a rate of change. So our rate of change here is 8.8 calories per 1 minute. So I'm going to plug in 8.8 into my equation. C equals 8.8 m. That would be our function rule. So we first thought about the equation y equals mx, or mx plus b. Okay, so that was our first step. How we can define the variables by y and x. And then the second thing that we did was substitute in the rate of change for m in y equals mx. Okay, so our rule here is c equals 8.8 m. Why don't you guys give this a try on your U-Try? Try to think of variables that could represent Matt and Sam. In fact, I would like you to use M for Matt and S for Sam. Try to translate this sentence. Translate this sentence, and keep in mind y equals mx. Go ahead and give it a shot. Alright, so that brings us to the close of our lesson. Just remember, we're still determining if a relation is a function, but today's lesson specifically focused on creating relationships that represent functions and still making sure we can tell the difference between linear and nonlinear. That was throughout all the examples. If you have any questions, please let me know, and you can go ahead and start your practice.